Sasa ndio nimengoja. Si zote zilikuwa bedsitter, but lakini hiyo ya 10 ilikuwa
Now, welcome everyone. Let's continue with our class. We continue looking at elliptic curves. Just a minute. Okay, we continue looking at elliptic curves. So far, we've looked at how to add points on elliptic curves. We've seen how to double points. Suppose you're given A, point A, you can double it to get point B, 2A. And if you have 2A, you can double to get 4A. You have 4A, you can double to get 8A and so on. So that is called point doubling. We can do that on elliptic curve. So we saw how to tackle elliptic curves on integers, and then in the last lesson we looked at how to deal with the elliptic curves on integers mod n. So we've seen how the two elliptic curves look like on integers and on integers mod n. So today we want to proceed. This time we want to see how to multiply points on elliptic curves by scalars. A scalar is just a number, so we want to see, supposing given point A, can you get 5A? Can you get 17A, and so on? So we begin with a very easy part where we begin by taking our scalar to be -1. And so we want to multiply a point by -1. So that is just the same as getting the inverse of point A. So when you are multiplying by point A by -1, I've said that is the same as getting the inverse of -A. So if this is -A, if this is point A, mod 7, and then you multiply by -1, the sign of y-axis, a point on the y-axis, the one that changes. So what you get as your new point is this. So what, in fact, that is just same as getting the inverse of A. Because the inverse of A will just be 1, then -4. And since we are doing it mod 7, this negative number, we make it positive by just adding 7 to it. And you get this 3. So this is now the new point that you get after multiplying the original point by -1. So multiplying by, if -1 is the scalar, then that is very easy. Just the same as getting the inverse of that point. The final example on that, supposing I'm given A this, and I'm supposed to get -A. In other words, I'm getting the inverse of point A. And so the inverse of point A will just be 5, -3. But I'm doing it mod 7. So the -1, I'm supposed to change it to positive by adding 7 to it. And then I have this as the new point. So this is the inverse of A. Now, all these points are on the curve. Whatever you do on a point, what the new point you get is on the curve. And we said elliptic curves form a group, and therefore they are closed on addition. And so their inverses are also there. And if you are to multiply those points by scalars, the new point you get again would be on the elliptic curve. It can never be outside. So for instance, if I'm given this point A, which is 1 for us in this example, I multiply it by 2 to get it to A, This 2a will also be on the elliptic curve. It's one of the points on the elliptic curve. If I multiply it by 70 to get 70a, 70a will still be on the elliptic curve. So, and again, we say that it's closed under a scalar multiplication. It is closed. So, in fact, what we are saying is this: to get 70a is the same as adding a 70 times. So, still closed under addition. You're adding a plus a plus a. In fact, the easiest way to do this, supposing just before you go to the code, and that is what we shall be doing, supposing I'm supposed to get 8a, if that is a question. What I'll do, the first thing I'll do, I get 2a. Then on this 2a, I'll add a to get 3a. Get 3a. Then this 3a, I'll add a to get 4a. And then this 4a, I'll add a to get 5a. This 5a, I'll add a to get 6a. And then this 6a, I'll add again a to get 7a. And then finally, I get 8a. So I can do that. Or if you want, you can come up to 4a. You can come up to 4a and just add 4a plus 4a. And you are at 8a. You can still do that. Can still do that. So that is what the code will then be doing. What the code will be doing will be adding, be doubling, and then adding. Doubling, then adding. That's what the code is supposed to do. So for us, therefore, to write a code to assist us do scalar multiplication, we must first of all know the formula for doubling of points and then adding of points. The formulas that we talked of the other day. So those formulas for point addition and doubling are very crucial, therefore, going forward, because that is the only way you can double. You can multiply points by scalars and so on. So let's look at the code that does this. I do not want to do it physically, but of course you can do it physically. You can do it physically, but it will be long. So just before the code, I've noted here that to get any p, where n here is the scalar, we're multiplying this point p with. So n is our scalar and p is the point on the elliptic curve. And p is this point on the elliptic curve. What the code will do is that it will utilize double and add approach. Double and add approach. And this is what will assist us going forward. So you double, then add. What we realize is that the formulas are different for doubling, and then adding, they're also different. For example, if you're adding 2a plus a, the formula here is different from if you're adding a plus a. The formulas are different. This one is doubling, and this one is just normal adding. Now, so I've given, this is the code. This part is to define the point, giving us x and y, and also infinity. So this one, the infinity here, the flag infinity indicates if a point is a point at infinity. That is what it will be doing. But then this is where the code begins implementation. So this part is just to identify if a point is a point at infinity, is at infinity. So this function is to determine if the point is at infinity. That's what this function will be doing. That's what that function is doing. Then I have this other function for getting the inverse, modular inverse. And it's using the extended Euclidean algorithm to do that. Getting the inverse. When are you getting the inverse? You know the formula for getting the what? For the gradient. The formula for getting the gradient. If is 3x squared plus a out of 2y. And so we are getting the inverse of this denominator. We're getting the inverse of this denominator. And then the inverse of this denominator, you're multiplying by the numerator at every point. So this is what this function is doing. This is when you are doing point doubling. And again, the formula, if you are doing point summation, adding, the formula for the gradient is change in y over change in x. And again, this will be a number whose sometimes the inverse has to be obtained. The mod n, mod p. The inverse has to be obtained mod p. So again, this inverse is obtained here. And it's using extended Euclid's algorithm. And look at what is here. That if it's less than 0, if the result you get is less than 0, you add m to make it positive. That's what this is saying. If t is less than 0, then t becomes t plus m. This is how you read this. If t is less than 0, supposing you obtain your t to be -3, then what does, so you obtained t to be -3, so what does t become? This point says t becomes t plus m. So -3 plus your mod, supposing mod was 7, that's -3 plus 7, which is 4. So that's what this part says. So this t, therefore, is the inverse. Is the inverse there. Because that now, but it begins from here. Begins from there. It begins by saying, let t be mutable. And initially, you're initializing t to be 0. The initial t is 0. So let t be mutable, but you begin by letting it be 0. Let new t be also be mutable, but you initialize it at 1. Let r be mutable. Initialize at m. New r be mutable also. Initialize it at the remainder of a on division by m. So that's how you should understand this. So it begins at that. Then it says something here. While a new R, you say new R, where is the new R? 1, 2, 3, new R. No, new R is the last one. New R is the last one. And this new R, you made it A, the remainder of A on division by M. It means by saying, while a new R is not equal to 0, hello, can you hear me?
Yes.
Yes, so if you can hear me, it's okay. So while new R is not equal to 0, you enter some loop. You enter some loop and do some calculations. What are the calculations? The calculations are, you see, what was R? R was mutable and was made to be M. Initially, was made to be M. And R, new R, was made to be the remainder of A on division by M. So, while this new R is not equal to 0, you let the quotient be this R over new R, the quotient. Then you let T. What was T? T was 0 initially. But now our new T now becomes the original T minus the quotient, this quotient multiplied by new T, multiplied by new T. Our new T was where? Was 1. Then you come, and then what about R, new R? Our new R becomes the old R minus quotient terms, and so on, and so on. So this process continues until R is 0. New R, until new R is 0. This process continues until new R is 0. But while new R is not 0, the process continues. Oh, there's something I forgot here. After you've done this, you see the initialized values for that. Then after initializing those values, you've calculated the quotient, then used it now to find T. And now T is no longer 0. You've now calculated T. After calculating T, there's some swap you do, the mutable T and the new T. You swap them. What was mut T was 0, and the new T you've just calculated. Another T. This now becomes the new T. But for this, you're using the one you had already initialized to get now the new T. And then there's some swap there. Then you come and find R now. Now the new R. And this new R is the one we want to proceed until you get 0. Want to do until you get, so you get the new R again. New R is obtained as this. So if you have values, you can take values and then just do examples. But that is how the code will be doing. So you get the new R. So if this new R is not equal to 0, the process again begins. The process again begins. You again come here, find the quotient. Find the quotient. There was some swap. There was some swap where you got R, this swap here. And the new R now becomes this. The new R becomes this. So it's R over the new R again to give you the quotient. Then again, find the new T, find the new R, do some swap. If the new R is not 0, again, repeat that process. Now, if when the new R is 0, whatever you'll have as T above becomes the inverse. Becomes the inverse. And if it's less than 0, you add M to it. So that is what this code will be doing at that point. That function will be doing at that point. Then we have this elliptic add. So this is to add point P and Q where these 2 points are not the same. Where these 2 points are not the same, this is going to add. And we know the formula. But then it begins by saying a point at infinity. So that means you have infinity, which is identity. Then you add Q. The result will be Q. So it says, if P is a point at infinity, return Q. So Q becomes the result. Then it proceeds and says, what about if Q is the one that is a point at infinity? So that means you have P plus the point at infinity. The result should be P. It says, return P. You see, these are 2 different points. These are 2 different points. One is infinity, another one is Q. So the result should be Q. And one is P, another one is infinity. So the result should be P. Now, if that is not the case, if none of them is infinity, but if they are on the same vertical line, the X values are the same. Let me say 3, 4, and 3, 8. These are 2 different points, but they're on the same vertical line. 1, 2, 3. So one is 0.34, another one is 0.38. They're on the same vertical line. So if they're on the same vertical line, then their sum is point at infinity. So now it's saying, if the X value of P is the same as the X value of Q, no matter what Y is, for instance, if the Y value of P is not equal to the Y value of Q, or if the Y value of P is 0, if the Y value of P is 0, then the result will just be point at infinity. So what this means is this. What this means, supposing I have Y values which are not the same, as in this case, but the X values are the same, the result is a point at infinity. In fact, it would be the same thing that if I had the Y value of one of them being 0, for instance, let me say 3, 0, and even 3, 8, still this is a point at infinity. So this function is doing that summation. It's doing that summation. Is identifying if values have the same, if points have the same X value, and then it has to return point at infinity, and so on. Now, where these conditions are not met. Why are these two conditions not met? Then it means now it proceeds to calculate if the p-values, let me say x value for pz and y value for pz, x value for q and y value for, so these are different points. So then it proceeds to calculate lambda. And this lambda is calculated as 3 multiplied by x1 times x1. So this is same as 3x1 square plus a. Then the result is multiplied by the inverse of y1. And what is this? What is this? This is if it's the same point. If x1 and x2 are equal, and y1 and y2 are equal. If x1 and x2 are equal, y1 and y2 are equal, that means the same point. And you know the formula is always supposed to be 3x squared plus a out of y to y1. Let me just say that. So then instead of doing this, the program is doing it as 3 times x1 plus a, then gets the inverse of this, and this one has been done above, mod inverse of 2y1, and then reduce it mod m. Then the entire result, after this multiplication again, reduce it mod m. So that gives you the gradient. That gives is the same point. P plus P to the same point P plus P. And then from there now, and again, another gradient, supposing there are two different points, then you have change in y over change in x. But instead of that, get the inverse of the denominator and multiply by the numerator. Get the inverse of the denominator, mod m, and multiplied by the numerator. The result, reduce it mod m. That's what it's doing at that point. So at this point, we just get the gradient. Gradient, whether the point is the same or whether the points are two different points. So I just put them under the same function. So the same function, the function just itself, it will be telling, it can tell that this is the same point. So if it is the same point, it knows the formula to use to get the gradient. It knows that the formula will be that if it's the same point. If there are two different points, it knows that then it's going to use this formula to get the gradient. That's why it says else. Else. Else means if this condition is not met. If this condition is not met, then it will perform the gradient using this method. Now, after getting the gradient, we now proceed to get x3 and y3. And x3 is supposed to be gradient square, gradient times gradient, minus x1 minus x2. Then the result, reduce it mod m. The result, reduce it mod m. What about y3? Y3 will be gradient into x1 minus x3 above. Then the result, subtract y1 and reduce the entire result mod m. Reduce it mod m. So you have x3, y3. So this function I said is doing point addition. It proceeds and says, if you find that the x3 value is less than 0, which is not supposed to be the case, if it's less than 0, proceed and add m to it. Else it means if this condition is not met, if it's not less than 0, it remains as x3. If it's not less than 0, it remains as x3. But if it is less than 0, you add m to it first of all to get x3. That's what this part means. What about here? The y. If y3 is less than 0, again, add m to it to get y3. Else, it remains as y3. So at that point, infinity will be false. What it means is, if you find a point at infinity, if the sum is a point at infinity, the code returns false. So I've been using none, so you can just interchange, say either none or what, and so you interpret it as point at infinity. Now, so that code is doing that addition of points. But the one that is doing scalar multiplication is this. This is the one that is doing scalar multiplication. Now, we want to multiply n by p. P is a point. So you begin by making the result mutable. The result of this multiplication, you let it be mutable and initially make it be infinity. So let the result be infinite, point at infinity. So you begin by that. So it will be changing as you continue doing the nick continues. As the program continues running, it will be changing from infinity to what the value is. So initially, let it be infinity, the result of this n times p. Then let add end be p. So that one, when we are adding, we want to add a point p to itself, for instance. So, but we begin by letting it be p, the summation. Then let mut n be n. So n again will be n. We know, for instance, you want to get 5p. You begin by n being 5, but it will be mutable, to be changing. So where does it change to? So we say, while n is greater than 0. So we want to go with it until this condition is not met. We begin by n being 5. Then it has to change until this condition is not met. So when this condition is not met, we get out of the loop. So we are saying while n is greater than 0, then we enter the loop. We enter the loop. But the loop will continue, we remain there until the condition is not met. Okay. So once we are done with the loop, we will get the result, and the result will be n times p. That will be the result. So if n and 1 if it equals to 1, if n equals to 1, again you enter the loop. So what do you do here? The result becomes, you add. This is elliptic add. This is a function we mentioned above. So it goes there, and then borrows the result. So the result comes from there. This function is above, elliptic add. So that is where it goes to get This is the function. So it borrows from this. So it requests this to perform. It requests this to perform that summation. So this is the one that is doing the formation, that summation. This one just borrows from there. So it's not doing it. So once, if n, or you see, if n is 1, then it means it asks, for instance, you have 1p, it will just ask for this one to give it, first of all, the result of this. Then if n changes to 2, if n changes to 2, again, it will ask for this to give the result. So this one will add 2p plus 2p. It adds 2p plus 2p. If n changes to 3, then it asks this one, this time to perform this 2 plus p to give it this. So this, it will just be asking for this one to do that. Okay, then we have the main function. The main function is where you initializing your values, putting value of n, putting value of a, and putting value of p, putting value of m, and so on. Now I've added points, notes here for that explains how the code works. So at your own time, you look what the explanations as you go. The good thing, the best way to look at explanation is look at how it works, how I've explained it works. Then you go back to the code and see it and understand the code, how it works. When you understand how it works, it becomes easier even to come up with your own. So let me share the code. And this is a code for scalar multiplication. And here it is. Now this is the main function. And I've asked it to compute and print the final result. What I want it to compute is NP. I've defined P, my point, and N, I want it to be 2. I can change it to 3, 4, 5, 6. N is the value you want, the scalar you want to multiply by P. Then the point is point, okay, the curve. The curve has this. A is 4 and B is also 4 mod 3, 13. So if I ask it now to give me that, it's supposed to give me 2p. It has written here and said, point 2p is 79,176, and then it has confirmed that this point lies on the curve. Because I had asked it to print, if point P is on the curve, it will print is point is on the curve. To print that the point is on the curve. I saw that right. I said, is the point on the curve? Yes. Is it the point on the curve? That's the question. Is the point on the curve? Then it is supposed to respond whether yes, true or false. If the point is on the curve, so it's supposed to. But of course, this point will be on the curve always, because just taking a point on the curve and you multiply by. Okay, there are two scenarios that this point will be on the curve, and if it fails, then it will be a point at infinity. It becomes a point at infinity. and the point at infinity is never on the curve. Now let's just change and see whether it will give us 10p. I want it to give us 10p. So to get a 10p, it's going to do 2p, then 2p plus 2p gives us 4p, then 4p plus 4p will be 8p, then 8p plus 2p gives us 10p. So it's supposed to do all those steps. It has done 10p and it has given us the result. And this result again is on the curve. So that is how it does. So you look at this code later and try to customize it. Try to, first of all, understand how it works. These symbols, how they work. The good thing is that when you understand how it works, you can even use the same technique to do another code similar to this, not necessarily this, but one that can work similar to this. Now, so that is about scalar multiplication. We multiply a point by scalar, and added under this, understanding the Rust code. Under this, I've explained how the code will be working and so on. Even this part, I'm showing that point addition, what is happening when p is at infinity, no, q is at infinity and p is at infinity. No, if point p and infinity, where q is now is the one infinity, and then the result will be p. And when it comes to point doubling, I've shown the formulas that they are there, they're in the code. And that is exactly what is happening in the code. Then I will explain how scalar multiplication is done at this point. Then I will explain that at this point, it checks if the point is on the curve. Checks if the point is the curve. I don't know whether you saw that. I don't know whether I showed you where it's checking if the point is on the curve. Okay, is that? Oh yeah, it's in the main function. The main function is the one that is doing that. And how does it do this? If you see, for you to check if the point is in the function, what it does is that it substitutes the value of x and sees if it gets the same value of y that it has. Now, another concept in elliptic curve is the Hess bound, or the Hess bound. And this theorem tells us the approximate number of points that you can get on the elliptic curve, the approximate number of points. This is very important in security because then once you know the approximate number of points you have on the elliptic curve, you know you require an elliptic curve that has so many points. You require one that has so many points. So it's good to know the approximate number of points you are working with for security reasons. So what does it say? The number of points on the elliptic curve, n, the number of points on the elliptic curve, n, lies within this range. In other words, if you're doing it mod p, then the number of elliptic points, supposing I'm doing it mod 7, So the number of points on the elliptic curve mod 7 will not be far from this. 7 plus 1, and then plus 2 multiplied by the square root of 7. And then also will be less than or equal to 7 plus 1 minus 2 multiplied by root 7. So they cannot be too many from here. They must be in this range. Those number of points will be in this range. They can never be more than this value, and they can never be less than this value. The least they can be is they be equal to this value. The least they can be is they can be equal to this value. And the most they can be, is they can be equal to this value. So they're always very close to n to p. They're always very close to p. So if p is, for instance, 11, then the number of points will just be around 13. They cannot be very far. Just be between 11 and 13, around there. If they go down a bit, they not go very far from 11. Suppose you are doing it mod 11. So the number of points will not be very far from this 11. This is what this theorem is saying. That they not be very far from this 11. Let's just see the maximum they can be. Let's see the maximum they can be. The maximum they can be is 11 plus 1, which is 12. Then plus 2 multiplied by the square root of 11. Or the square root of 11. The square root of 11 is 3 point something, 3.3. So you multiply that by 2 again. When you multiply this by 2, you get around 6. So this 6 plus 12. And then you get, if they were to go very far, then they will be 18. If they are to go very far, they will be 18. So using this theorem, you can roughly tell the number of points you're expecting a certain elliptic curve to have. So you can see then using a curve that has mod 11 is very insecure because you're only dealing with about 18 points. At most 18 points. They could even be less. So those points, if you're doing your security, you want to, supposing you're doing encryption using 18 points, somebody can easily get to know what your original message was by just using brute force, trying every point. You see, you have to come up with a secret key. So somebody can easily tell what your secret key is. And try this point, try this point, try this point. Try all the 18 points. If there are 18, or if there are 5, try all the 5 points. So then you require a bigger p-value. You require bigger p-value so that you have several points. So that is the importance of this. Theorem. It tells us the approximate number of points we expect a certain elliptic curve mod P to have. So I've said at this point, it provides an estimate for the number of points on the elliptic curve. An estimate, just gives us an estimate. It doesn't tell us exactly how many points there are. Of course, we did a code that was giving us the exact number of points. But if you don't have that code, of course, you can estimate the number of points you expect. But as I said, if P is something 7, you're not expecting these points to be very far from 7. Just close to 7. So I've said, given an elliptic curve E of a field FP with P as a prime number, the number of points n on this elliptic curve including the point at infinity, would satisfy this inequality. In other words, it will be within this range. This inequality means that the number of points on the elliptic curve does not deviate too far, from p plus 1. So if p is 7, then they don't deviate too far from 8. They not go far from 8. To the left or to the right, they don't go far from 8. To the left or to the right. So what are the expected number of points? We expect p plus 1 points, actually. If p was 7, we expect 8 points. This is the expected number of points. If they were to be uniformly distributed, that's what we expect. But now, if there could be any deviations, then the deviation will be this to the right and to the left. That will be the deviation. That's what we are saying. The expected number of points are these. These are the expected number of points, p plus 1. But then if there will be any deviation, then the deviation will be 2 multiplied by the square root of p, to the left or to the right. So that is in cases where points are not uniformly distributed. In those cases. But in most cases, these points are normally uniformly distributed. And in that case, if p is 7, then I just expect that I'll be having 8 points. If p is 13, then I expect I'll be having 14 points. If they are uniformly distributed, if there are no deviations. So what is the application of this? Where do you apply this theorem? I've said this theorem can be applied in elliptic curve cryptography. And how is it applied is essential for the security of elliptic curve-based cryptography or crypto systems. Because in these crypto systems, we are securing our crypto system using encryption and decryption, and we are doing that using picking a point. A point becomes, of course, our key, and that becomes our private key, and from this we also have a public key. And so we don't want the enemy to know what our private key is. And so we don't want to have very few points where the enemy will be trying this point. If it fails, tries another one, and then tries another one, and then the enemy tries all the points. If there are only 8 points, the enemy may want to say, let me just try. There are only 8 points. Then the enemy tries and gets the correct result and gets our secret message. And the message that was not meant for him, the enemy gets by just trying. But if you have very many points, the enemy may not have the courage to begin trying every point. Try this, try that, try this, and so on. So you'll discover later that the elliptic curves that are used in real life situations, they have very many points, very many points. If you were to begin trying each of them, you'll want years, you'll need years to try all those points. You'll need years. They may not even be 3 years or 4. They may even be 300 years. It may require even 300 years trying each of the points. Nobody has all that time. And that is why now they become secure, because of that. Not saying they are very secure, but for some reasons, they are somehow secure. Now, so therefore, because of that, they can be applied in digital signatures and in encryption and decryption. Can also be used in algorithms to efficiently count the number of points on the given elliptic curve of a finite field. So that is how we apply that. Now, another very important point, another very important thing in the elliptic curve is how do you find the order of a point on the elliptic curve? And also, how do you find the generators? How do you find the generators? Let me just define what the order is. In group theory, when we looked at groups, we said the order of an element and addition, the order of an element A, the order of an element A is n. If A added n times gives you the identity, So it means if you had to add A 3 times and then get the identity, then it means the order of A is 3. If you were to add A 5 times, then get identity and addition, if that gives the identity, then the order of A becomes 5. That is what we learned about groups and addition. And since the elliptic curves are groups and addition, they're not groups under multiplication, they're groups and addition. Since the groups and addition, again, we are saying the order of an element A is the smallest integer, which when added A those number of times, you get the identity. The identity this time is pointed at infinity. So for instance, if A plus A plus A 3 times gives you the identity element, and then the order of A is 3. That's the order of A. If adding A 4 times gives you the identity, then the order of A is 4. That's what it means by order of an element. It's good to understand it before we do the examples. What about generator? And again, I go back to group theory, groups. And when do you say that an element is a generator of a group? We say that an element under addition, and I'm again referring to groups and addition because elliptic curves are groups and addition. So under addition, element 3 of a certain group will be a generator of this group if 3 generates all the elements of the group. If 3 generates all the elements of the group. Let me say, for instance, I'm talking about a group mod 7. Let me say I'm talking about group mod 5. Mod 7 is too big. Let me talk of mod 5. Mod 5, this group has additive. Then this group has 5 elements. 3 becomes a generator if 3 generates all the elements of this group. By adding, for instance, when you add 3 once, you get 3. If you add it twice, it gives you 1. So 3 is not a generator. No, it is. Let's continue. That's not giving us the identity. So we add until you get the identity. The identity of this element of mod 5, group mod 5, we're talking of this, Z mod 5, the identity is 0. The identity is 0. So we add it until we get 0. Now, 3 times will be 4. I'm doing it mod 5. would be 4. Because this is, what is this? This is 9. 9 divided by 5, the remainder is 4. Or just add this plus 3. Okay? 3, 4 times. 1, 2, 3, 4. Would be 2. And 3, 5 times. 1, 2, 3, 4, 5. Would be 0. So you can see adding 3 to itself, you generate all the elements of this group. Because this group has elements 0, 1, 2, 3, and 4. These are the elements. And those are what will be generated. We generate 0, 1, 2, 3, and 4 by just adding 3. This is what we mean by a generator. So a generator is that element, you add it to itself a number of times, and it will generate all the elements of the group. Every time you add it to another, to itself, generates a new element, yes, until it generates all the elements of the group. So that's what I mean by a generator. And that is what it is even for the elliptic curves. So by a generator of the elliptic curve, we mean an element of the elliptic curve that would generate all the other elements. Not all elements are generators. Just a few of them. Just a few of them become generators. So I've said the order of a point P on the elliptic curve refers to the number of times that a point must be added to itself to reach the identity element. It refers to how many times that element must be added to itself to reach the identity element. That's what we mean by the order of an element. So I've just defined it there. So mathematically, we mean that if P can be added K times to get the identity, then K becomes the order of P. K becomes the order of P because you can add K, you can add P K times and you get the identity element. So this is how we abbreviate the order of P. So the order of P. So when you write that, it means what is the order of P? Why is the knowledge of order important in cryptography? It will affect the security of the elliptic curve based crypto systems. If the order of a point is large prime, then the crypto system becomes secure. The crypto system becomes secure if you're using a point. You see, we will be using these points as we're using them as either the encryption key or decryption key. So they become secret key and public key, these points. So you will then be choosing a point that has an order that is very close to P. An order that is very close to P. It must be an order that is very close to P. So if your P is 7, choose a point that has order close to 7. Must be very high order. So if you're talking about P being a number that is a very big number like this, very big number like that, that is your P. Then you choose a point whose order is close to this point. Not necessarily it must have the same order as P, but it should be close to P. Should be close. Should be higher order. higher order. It makes your crypto system secure. Unlike if the order is lower. And of course, when you're encrypting, for instance, I want to send you this message. Supposing I want to send you this message. What we'll be doing, and you'll see how we'll be doing it later. This message, I would first of all convert it to a point. I would first of all convert it to a point, this message. Convert it to a point. Then after converting to a point, that is now when you do your encryption and the decryption, because you now be adding this point to another point if you want to encrypt or want to decrypt, and so on. Of course, we do the same process of encryption and the same process of decryption, but the message has to be converted to a point. Then, of course, after converted to a point, you'll be choosing another point as public key, and then using it to get your private key. And the points you're choosing should be of high order. Should be of high order for security reasons. Now, let me just show you examples physically, and then we go to the code. Physically, find the order of the following points. In other words, how many times am I going to add this point to itself to get the identity? This is what the question is asking. Find the order of this point on this elliptic curve. And then it says, identify which of them are generators. We just want to see which of these points are generators. So which point among these would generate all the points on this elliptic curve? Of course, this elliptic curve, we've already seen using the hash that it's supposed to have around 8 points. Or if they go far from this, then they should deviate by 2, the square root of 7. That's what we expect. We expect the order of this curve, this curve, this elliptic curve, to have either 7 plus 1 points, 8, or they can slightly deviate by this. They can slightly deviate. So we want, by generators, we mean which of these points will generate all those points. But let's go very fast. First of all, find the order. So the order of 3, we're asking ourselves, how many times are going to add 3 to itself to get the identity? Then I decided to add 3 to itself to get a 3p. You'll do this later. You have a code. You have a code for doing this summation. This, in fact, that's what I was using. So 2p, I get this. P plus p, I get that. 3p means 2p plus p. P is this, and 2p is this. So when I add these two, I have this. Then I get 4p. 4p is, of course, 3p plus p. 3p plus p, and that gives me this. Now, I'm avoiding getting 4p by adding this 2p to itself. Because you may realize that that is not very good for you to do. It's not very good for you to get 4p by doubling 2p. It's not very good. Because what if 2p plus p gave you the point at infinity? If 2p plus p gave you a point at infinity as your 3p, you'll have reached what you wanted to get. You'll have reached the infinite already. But if you add this 2p to itself, it gives you a different point. A different point. It may give you a different point, but you are supposed maybe to stop here. You are supposed maybe to stop here. I don't know whether you're getting the point I'm saying. That in this elliptic curve summations, these elliptic curve summations, if you want to get 8p, for instance, that's what I'm saying. You want to get 8p, just add a point slowly by slowly, one by another. Just add p plus p, get 2p, then 2p plus p to get 3p, then 3p plus p to get 4p, then 4p plus p to get 5p, all the way up to 8p. Don't try to do it very fast. That you want to come here, so you just want to get 2p, then add 2p to itself, get 4p, then you want to get 4p plus 4p to get 8p. This is not correct. It's not correct, because at some point you may have skipped something very important. You may realize that at some point maybe 3p plus p was supposed to give you a point at infinity. So if it's a point of infinity, then 8p will not even be there. Or 8p is supposed to be something like 4p, for instance. Because if 3p plus p gives you a point of infinity, then it means this is 4p. So it means 4p plus p is supposed to give you p. It's supposed to give you p. Because you're taking the point at infinity, then adding p. It's supposed to give you p. So it means if you are to proceed, then this is what you call 5p. That's what you call 5p. Then it means plus p is supposed to give you 2p. So begin repeating itself. Because 5p is p, then plus p is supposed to give you 2p. So I think you've got what I say, what I'm saying. You don't need to move very fast to get 8p. That's why I was doing it step by step, just moving slowly by slowly until I get the identity. So I discovered when I was doing this, I did this, and I found that 10p was giving me the point of infinity. So it means, therefore, that the order of 3, 1 is 10. And I also note that the 3, 1 generates all the points. How many points are these? That's generated, okay, p itself, but when I add it twice, when I add it thrice, 4 times, 5 times, 6 times, 7 times, 8 times, 9 times, 10 times. So this has 10 points. This curve has 10 points. That's why he said it's supposed to have 8 points. Then there will be some deviation of 2√7. At most, we are not saying it must come up to there, but at most, what is √7? Just use my calculator. √7 is 2.6. So if I multiply that by 2, I get 5. And when I add it to 8, the result to 8, I get 13. So at most, if it was to deviate, the most number of points it could have is 13. But we've of course found that it has 10. It never reached there. It never reached there. So this point has generated all the points on the elliptic curve. This elliptic curve has only 10 points. Now you do the same for P, Q, and Q, you realize that at this point, the Y point is 0. So we already said that even in our code, that if the Y point is 0, then this point added to itself, you don't need to take a lot of time, it's supposed to give you infinity. If the Y coordinate is 0, it's supposed to give you infinity. And so that means, therefore, the order of this is just 2. You just add it twice and you get infinity. So this one does not generate the entire curve. It does not. What about this? Again, this one does not generate the entire curve, because you realize that 5p is the one that gives us infinity. And so on. So this, you don't need to do it manually. Of course, you can do it manually when you are writing your code, just to verify that your code agrees, the calculations of your code agree with your manual working. If you just want to verify. But once you have the code, then these calculations will do it using your code. So why is my code there for? My code is here. Now, what is the code doing? This code is just to find the order. So I say the Rust code determines the order of a point. That's what it does. So the one for doing generator is not here. I made them different. So this one is to do the order. So of course, that is what it will be doing. It will be adding a point to itself until it gets point at infinity. That's what it will be doing. So when it gets the point at infinity, then it says that it reads the order. Okay, so I've added notes inside this code. You can follow that. Of course, you have to get inverse when you're doing summation because the denominator must get the inverse of that and so on. And then for you to get the order, and then you begin adding a point to itself, add it to itself. And we have written here, add the points. Is that to find the order of G, I've said, first of all, make the current point be G. Then let the order be 1. Initially, just let the order be 1. Then enter the loop. Enter the loop and begin adding points to itself. And every time you do that, increment by 1. Increment by 1. So I added P to itself. I got 2P. Then I increment by 1. Now 2P plus 1. No, plus P. I get a 3P. Now 3P plus 1P. Get 4P and so on. Increment by 1. Just go step by step until you have the result. And once you get, I used this. I used -1, -1. Once you get -1, -1, what you have is the order. I use -1 because you cannot add, because when you're adding, you're supposed to get a point, X value and Y value. And when you talk of point at infinity, the X value and the Y value of this point is not known. Is not known. So once we reach -1, -1, we take that to be the point at infinity. Take that to be the point at infinity. -1, -1 is the point at infinity. So when you reach -1, -1, you exit the loop because you've reached infinity. So that is the only point I wanted to emphasize there. Because it must be a point on the curve. Of course, we know that infinity is not there. But I have used -1, -1. So that we have a point on the curve. Okay. And the rest are what we do, adding, just formulas for summation. Add this point to this point, add it to this, the same formulas. If the point is the same formula for doubling is there. Okay. So the code itself, I want the code that is for order, the order of a point. So the one I'm looking for. Is here. So if you want the order of a point. Now, so this one, I think, let me see what it runs. I thought I told it to run and give me all the points and their orders. Yes. So it does every point on the curve and the order of that point. So that is why it's long. Also, I wanted to give me, first of all, generate all the points. After generating all the points, I want it to give me the orders of every point. So that is why it's long. Otherwise, it's supposed to be a very short code. If you are just to give it a point, if you are to give it a point, then you ask it for it to give you the order of that point. That is different. But for me, I didn't want that. What I wanted is, first of all, it gives me the points, all of them. Then it gives me the orders of each. But you can write yours such that you give it the elliptic curve and a point. Then it gives you the order. You can also do that. Okay, so that is what I wanted us to look at today. So next time when we meet physically on a Thursday, maybe now we look at the code for generators. Thank you.
Thank you so much, Dr. Sakwa. And thank you to everyone else for attending today's session. Have a good night and see you on Thursday.